Okay, so today we're going to talk about limit laws. And so far in our study of limits, we really have been mostly dealing with limits on a conceptual level. And while dealing with limits on a conceptual level is nice, oftentimes it doesn't have that nice precision that we expect in mathematics. It's all kind of this, you're looking at a function, seeing like certain trends as the value of a function gets closer and closer to a value. But really, limits do have this fundamental, formal, rigorous understanding that you would expect it to have in mathematics. And we're not going to talk about the formal definition, but my hope here is that we're going to start to do this transition going from the imprecise idea of a limit, but as a trade-off, I hope to achieve the conceptual understanding to a more precise and algebraic sense. So, from my perspective, the idea of giving you the less precise form of a limit is to really start to fundamentally understand what limits are conceptually. And then once we've done that, we can start to actually look at more of the algebraic techniques for finding limits. And it no longer really becomes a guessing game, but it becomes, as I said, a very algebraic way of dealing with things. And we're actually going to begin talking about the more algebraic way to look at limits by considering what are known as limit laws. So all limit laws it's just a list of rules, which, as you can see, here they are. Big long list of rules that basically deal with limits. Now there are a number of conditions that have to be met, such as all the limits that you see have to exist and all that kind of stuff. And I do encourage you, if for those of you who are really nitpicky and want to know the precise conditions for this, to go grab your calculus textbook and look at those conditions that are set. But for the purposes of understanding calculus, and especially understanding the type of questions that you might see in a Calc 1 class, we'll just kind of do a brief overview of these limit laws. So the first law simply says that if you have a sum or difference, so I could have written this one line for addition, one line for subtraction. I just combined them. Basically, the limit of a sum of two functions will be the same as the sum of the limits. And then the second law says that if you have a constant multiple times a function, it's going to be the same as pulling that constant multiple out. And these two first laws here oftentimes go by a name known as linearity. And linearity is a well-established property in mathematics that has reaches that far extend limits. So when we talk about derivatives and integrals, they also have a linearity property. If you go to linear algebra, of course, it's kind of in the name, linear transformations have this linearity property. So it's a very common thing, and it will pop its head up over and over again. So I might as well make note of that. But limits also have these other properties. It actually turns out that if you take the product of the limit of a product, you actually get the product of limits, which is something that derivatives and integrals will not hold later. And same with this quotient system here. Note here that the denominator can't be 0 because obviously that would result in dividing by 0. Don't get me wrong, as we saw before, we do get indeterminate forms with a limit where you get a 0 over 0 when you try to actually evaluate this at the point there. But this is something different, so keep that in mind. Also, we can take exponents and roots. I just combine them into a single thing. So if you take the exponent of the function and then take the limit, it's the same as taking the limit first and then taking this. Again, we're assuming here that the quantities are defined here. So and specifically and they're real, because obviously when you take a square root or any even root of a function of a number that's negative, you get something that's complex. So we want to stay real in this particular example. And then these two laws down here are basically some very fundamental rules to kind of help us evaluate limits algebraically. As you'll see, in many cases, we will be able to do just direct substitution, which is what we do for c. So if you have just the function x here, you can plug in c, and you will get the limit. And then also if you have a constant function, which is just a horizontal line, so that's going to be, something that looks like this. Again, the c it doesn't really matter what c you have. The limit there will actually just be k. So we can take these. Again, I'm not going to go through formal proofs of these things since we still don't have a formal definition of a limit. But again, if you're taking a Calc 1 class, you can just use these as assumed rules that are true and to help you solve problems. So what are the type of problems that you might be asked, especially in a Calc 1 class? Because a lot of times these laws are more or less for proofs and for theoretical purposes, but and typically in a Calc 1 class, you're not going to be asked to do proofs, at least unless it's a particularly advanced class. So instead, you're typically given questions like this. So you might say, well, let's let the limit as x approaches 3 of some unknown function. We don't know what it is, but we know that the limit at 3 is going to be 8, and we know that the limit as x approaches 3 of g of x is equal to 4. And, I want to say, well, let's find this limit. Well, it turns out that by the quotient rule for limits, we can rewrite this as the limit as x approaches 3 of f of x over the limit as x approaches 3 of g of x. And if we do so, we can just directly substitute because we know that this one is just going to be 8. We know that this is 4, and 4, of course, is not 0, so that's good. It would be 2. Again, if this was 0, that doesn't necessarily mean that the limit is undefined. Something else could be going on, so just make sure that you're careful to make sure that the denominator here is not equal to 0. And then one final example, this is kind of going to be a mix of a whole bunch of different rules here. So we can actually just break this up into a number of pieces. We can take the 3 times the limit as x approaches 3 times of x. Okay, we can just say the limit as x approaches 3 of 2, and then we can also have the limit as x approaches 3 of g of x, and we can pull the squared outside the limit. So we're just going to break this into a few pieces. So because we pulled the 3 out, we know that this is going to be 3 times whatever this limit is here. So the rule for, again, if you just have an x, you can just plug in this 3 for x. So that's going to be just a 3. So it'll be 3 times 3 plus. Remember, if you just have a constant, okay, it really doesn't matter what the x is approaching. The limit will just be that constant. So that's just going to become 2. And then we know that the limit as x approaches 3 of g of x from above is equal to 4. And then we can square that. So what do we get? We get 9 plus 2, which is 11, plus 16, which will be 27. So again, these are the types of problems that you'll deal with when you deal with limit laws. Again, I hope that was helpful. And as always, have a nice day.